Welcome back to the course of Applied Elasticity. In the last lecture, we started our discussion on the kinematics of deformation. In this lecture also, we will continue with the discussion on kinematics of deformation. Now, first we are going to describe about the deformation gradient tensor. So, we are considering a body in the initial state where P to Q is a small elementary length d capital X. So, as discussed in the previous lecture, capital X vector denotes the position vector of the material point P in the undeformed or initial state, which upon transformation moves to the deformed or the current state where small x vector is the position vector of the corresponding point P prime. Now, d small x P to Q, this particular small line element deforms to P prime Q prime, which is defined as d small x, that is deformed line element. Let us choose the length of the undeformed line element d capital X vector to be d capital S and length of the deformed line element d small x vector to be d small s. The displacement is defined by this quantity u, which is small x vector minus capital X vector. Now, the deformation is completely characterized with the help of a tensor known as deformation gradient tensor, which is described by f, and through this particular transformation law, d small x is equals to f vector acting over d capital X for any small elementary vector d capital X in the initial state. If we act f, the deformation gradient tensor, on that d capital X vector, this will result the small elemental line element in the current state or the deformed state, that is d small x. From geometry, d small x can be written as O q prime minus O p prime. You can see p prime to q prime is small dx vector. So, O to q prime minus O to p prime defines the d small x vector. Now, O to q prime can be written as O to q plus q to q prime, where O to p prime can be written as O to p plus p to p prime. Now, O to q, this is nothing but capital X plus d capital X, O to p is capital X, O to q prime is small x plus d small x, O to p prime is small x. Substituting all this in this equation and cancelling this capital X, this would become d small x is equals to d capital X u at capital X plus d capital X comma t minus u at capital X comma t. Now, if you try to recall the definition of the second order displacement gradient tensor, the gradient of any vector u, gradient of u can be defined as grad of u which is a second order tensor acting over this dx is equals to u of x plus dx comma t minus u of x comma t. So, by definition of the gradient of a vector which is a second order tensor, which we are naming here as displacement gradient tensor, with the help of that, this expression can be written as d small x equals to d capital X plus grad u acting over d capital X. Now, with the help of this, we are going to define the deformation gradient tensor. Now, this first term d capital X, this can be written as identity tensor I acting over d capital X by the property of the identity tensor, and then combining both the terms, d small x would result identity tensor I plus gradient of u total second order tensor acting over the d capital X undeformed line element, and this is the deformation gradient tensor f, which is equals to I plus grad of u. So, d small x is f times d capital X, or d capital X can be written as f inverse acting over d small x, where f equals to I plus gradient of u, and this gradient operator is defined in the material or initial description. So, this refers to del xk. The derivative is with respect to capital X components in the definition of deformation gradient tensor in the initial or Lagrangian description. Now, coming to the components of this f vector, f tensor. So, f equals to I plus grad of u. So, we can write f I j as component of I, which is delta I j Kronecker delta, plus del u I del capital X j. As I had already told, this gradient operator refers to the partial derivative with respect to capital X. So, f I j, the components of the deformation gradient tensor, is equals to delta I j Kronecker delta plus del u I del x j, and this j is called determinant of f, which is called the Jacobian of the motion. Determinant of f is called Jacobian of the motion, and if j is not equals to 0, then only the f is invertible. So, it is possible to define d capital X as f inverse d small x only if determinant of f or j Jacobian of the system is not equals to 0. Now, in this particular spatial description, when f is written as a function of small x, for that case using a similar approach, it can be shown that f equals to I minus gradient of u, but here this gradient is defined in the spatial coordinate in the spatial description. So, that is why I have added a small x in the subscript of grad operator. This refers to partial derivative with respect to small x component del small x k. So, this is the definition f inverse I j, which would be delta I j Kronecker delta minus of del of u I del small x j. This partial derivative in this gradient is with respect to spatial or deformed coordinate vector. Now, coming to the definition of isochoric deformation. If we are having a deformation for which determinant of f or the Jacobian of the system is equals to 1, then during that deformation no change of the total volume of the continuum is allowed. So, for such cases, such deformations, we call it to be isochoric deformation, because this term isochoric refers to the case of constant volume. No change of the total volume of the continuum is allowed for the isochoric deformation, and that can be achieved if determinant of f or Jacobian of the system is equals to 0. Now, coming to the homogeneous deformation. So, if the deformation gradient tensor is same at every material point of a continuum, then we call that to be a homogeneous deformation. For such cases, f is only function of time, it is not function of capital X, the material point coordinate. For all the material coordinates, material points, we are having same f, which only changes with time independent of x. For such cases, this is called homogeneous deformation. So, deformation is same for all the material points, whereas for the case of non-homogeneous deformation, f is function of both capital X material point coordinate as well as time. And in this particular case of non-homogeneous deformation, all the material points do not deform in the identical manner. Now, coming to a very important theorem called polar decomposition theorem. This particular theorem states that any real tensor f with non-zero determinant, means j is not equals to 0, can be decomposed or can be written as a product of a proper orthogonal tensor Q and a symmetric positive definite tensor either U or V. Now, what is orthogonal tensor? That was already defined in the first week, whereas what is symmetric positive definite tensor? Symmetric tensor we had defined T equals to T transpose. If this identity is satisfied, then T is a symmetric tensor. Now, a tensor is called positive definite if all the eigenvalues of the tensor is are positive, then we call the tensor to be positive definite tensor. So, U or V being two such positive definite tensor and Q being an orthogonal tensor, f can be written as q times u, or f can also be written as v times q, where u and v are known as the right and left stretch tensors respectively. So, in any deformation, using the polar decomposition theorem, we are decomposing the deformation into two parts. Q is responsible for rotation of the body, whereas u or v is responsible for the stretching, change of shape of the body. So, the total deformation can be having first stretching followed by rotation. It can also have first rotation followed by stretching or change in shape. So, that is what the physical significance of the polar decomposition theorem is. And pre-multiplying this equation f equals to q u equals to v q with q transpose on both the sides, we can show that u is equals to q transpose v q, or we can also show that v is equals to q times u times q transpose. Now, after deformation, we are coming to the definition of different strain measures. The first strain measure which we are going to discuss is the Cauchy-Green strain measure, which is known as C, Cauchy-Green deformation tensor C. So, we are considering the same body where undeformed line element d capital X is deformed to d small x with the help of deformation gradient tensor F, which defines the mapping from initial state to the current state. So, d capital S is the P to Q, the undeformed line element length, whereas d small s is the deformed line element length P prime Q prime. Now, as ds is the length of d capital X vector, we can write d capital S square is equals to d capital X dot d capital X. With the help of indicial notation for dot product of two vectors, this can be written as dxi times dxi. Now, if you also write d small s square, the square of the length of the line element in the current state as d small x dot d small x. Now, d small x is nothing but f acting over d capital X. So, this quantity is f d capital X dot f d capital X. And if you try to write this in the initial notation, this first f acting over d capital X is written as f I j d capital X j, second one is written as d f I k d capital X k. So, d capital X j d capital X k are two vectors, f I j f I k are two tensors. Now, we are rewriting this f I j f I k as f transpose j I f I k. Why? So that we can take the product of these two. The second index of the first tensor is I, first index of the second tensor is I. In this fashion, we can write this as product of f transpose f. So, d small s square is equals to d capital X j f transpose f j k d capital X k. This can also be written as dx dot f transpose f acting over d capital X. And this quantity f transpose f, this is defined as C, the Cauchy-Green deformation tensor. C is defined as f transpose f. Now, this particular Cauchy-Green deformation tensor is known as right Cauchy-Green deformation tensor, which is defined as f transpose f, and component wise C I j is f transpose I k f k j. By definition of f as del x k divided by del capital X I times del x small x k del capital X j. This would be the components of C I j. Now, if you recall, the f was also defined as I plus gradient of u. Now, if we replace that expression of f in the definition of C, so C is f transpose f. So, transpose of I plus grad u multiplied with I of grad u. If I expand this, so transpose of I plus grad u is transpose of I plus transpose of grad u separately, and transpose of I is same as I only. So, if you expand this, we will be getting 4 terms: I plus gradient of u plus transpose of gradient of u plus product of transpose of gradient of u into gradient of u. Now, this is the definition of right Cauchy-Green deformation tensor. In the same fashion, we can define another Cauchy-Green deformation tensor, which is named as left Cauchy-Green deformation tensor and denoted by B tensor, which is nothing but transpose of C, and it is F times F transpose. So, right Cauchy-Green deformation tensor C is F transpose F, whereas left Cauchy-Green deformation tensor B is F F transpose. Now, with this definition of deformation gradient tensor and right and left Cauchy-Green deformation tensors, we will be trying to solve few example problems. So, let us consider this deformation mapping: small x1 is equals to capital X1 plus 2 capital X3, small x2 is equals to capital X2 minus 2 times capital X3, small x3 is minus 2 capital X1 plus 2 capital X2 plus capital X3. You need to determine the displacement components in both Eulerian and Lagrangian formulation. You also need to determine the F, C and B tensors. So, first starting with part A, the description of the deformation is given in the material coordinate, because small x are given to be function of capital X. The displacement components u is defined as ui equals to small xi minus capital Xi. So, with the help of this definition of displacement component in the given material description, small u1 is small x1 minus capital X1, which is 2 times capital X3, and so on. In the same fashion, you can obtain all 3 deformation components in the material description, where they are function of capital Xi. Now, for finding u in the spatial description, we need to invert the equation of mapping, given mapping. So, small x is equals to this tensor 1 0 2 0 1 minus 2 minus 2 2 1, this matrix times capital X1 capital X2 capital X3. This matrix refers to the deformation gradient tensor. Now, if you invert this matrix, then capital X1, capital X2, capital X3 vector can be written as function of small x1, small x2 and small x3 vector. So, this particular 1 by 9 times this matrix is nothing but inverse of this particular matrix. So, with the help of this F inverse matrix, we can write capital X1, capital X2, capital X3, the material position vector components, as function of small x1, small x2 and small x3. Now, if we try to write u, the displacement component, we had already described u in the material description as function of capital Xi. Now, we know what are these capital Xi's are as function of small xi. So, if you replace capital X1, capital X2, capital X3 as function of small x components in the expression of this u and simplify them, you will be getting the displacement component u1, u2 and u3, all 3 displacement components as function of small x1, small x2 and small x3, that is in the spatial description. Now, coming to the second part, as I had already told, small x is equals to this matrix times capital X, and that matrix is nothing but the matrix of the deformation gradient tensor, because by definition d small x vector is equals to F acting over d capital X vector. So, this particular matrix is nothing but the matrix of deformation gradient tensor F. Now, you can easily find out C, the right Cauchy-Green deformation tensor, by taking the product of transpose of F with F, that will come out to be this, and B, the left Cauchy-Green deformation tensor by taking the product of F and F transpose, which will come out to be this. And if you compare them for this particular problem, both right Cauchy-Green deformation tensor and left Cauchy-Green deformation tensor comes out to be same, because this is a symmetric tensor. Now, coming to the next example problem, where we are given a square block of sides 2 unit, which is initially centered at origin 0, 0, 0. you are asked to determine the deformation gradient tensor f and sketch the deformed square if the deformation mapping is given as small x1 equals to 3.5 plus capital X1 plus 0.5 capital X2, small x2 is 4 plus capital X2 and small x3 is equals to capital X3. So, this is the given deformation mapping which is defined in the material time frame. By definition of the components of the deformation gradient tensor, Fij is del small xi divided by del capital Xj. So, from that you can easily find out the deformation gradient tensor f as this. So, the first component of f is what? Del small x1 del capital X1. Second component is del small x1 del capital X2 and so on. Like that you can obtain all the components of this deformation gradient tensor, and that would come out to be 1.500100001. Now, coming to the displacement fields, u1 is equals to small x1 minus capital X1, which is equals to 3.5 plus 0.5 x2. This can be obtained from here. Small x1 is equals to 3.5 plus capital X1 plus 0.5 x2. If you take capital X1 on the left hand side, that would give us u1, the first displacement component, which would be 3.5 plus 0.5 x2. In the same fashion, we can obtain the second displacement component u2 to be a constant 4 from this, and third displacement component u3 to be small x3 minus capital X3, which is equals to 0. So, here only one displacement component is function of the position vector capital X2, rest two u2 and u3 are constants 4 and 0. Now, we are first sketching the given square in the undeformed configuration. So, center was given at 0, 0, 0, that is at the origin. A, B, C, D, this forms the given square of side length 2, length of each side is 2. So, the coordinates of 4 corner points A, B, C, D are -1, -1, 0, 1, -1, 0, 1, 1, 0 and -1, 1, 0 respectively. Now, we had already defined the displacement components u1, u2, u3 in the material frame, material description, and with the help of this we can obtain the deformed coordinate. So, u of any point is defined as the ith component of u is small xi minus capital Xi. Thus, the capital Xi plus ui, this will give us the deformed location. We know the undeformed material coordinate for all these 4 points A, B, C and D, and we also know the displacement vector. So, adding the displacement vector with the undeformed coordinate xi, we can get the deformed coordinate small xi. So, for first point A, undeformed coordinate is given to be -1, -1, 0, and the deformed coordinate would come out to be 2, 3, 0. How is it coming? So, if you are considering u of A, the displacement of point A, the first component of that is 3.5 plus 0.5 times x2, the position vector, second position vector for point A, which is equals to -1. So, this would be 3. So, -1 was the undeformed coordinate, corresponding displacement is 3. If you add both of them, you will be getting 2. The second displacement component is 4 for all. So, this second position vector component is -1 plus 4 would result 3, and third displacement component is 0. So, here that remains same. So, like that the undeformed coordinate -1, -1, 0 for point A changes to deformed location 2, 3, 0. In the same fashion, for point B, the deformed coordinate can be obtained as 4, 3, 0. For point C, the deformed coordinate can be obtained as 5, 5, 0. For D, deformed coordinate can be obtained as 3, 5, 0. Now, we know the complete deformation mapping and obtain the location of all 4 deformed points A, B, C, D. Let us say A prime, B prime, C prime, D prime, they are new names. If we sketch it, that will be looking something like this. So, A prime is 2, 3, 0, B prime is 4, 3, 0, C prime is 5, 5, 0 and D prime is 3, 5, 0. You can see A prime, B prime and C prime, D prime, these are parallel to x axis, whereas B prime, C prime and A prime, D prime, these two sides will no longer remain parallel to y axis. So, from a square it is getting changed to a parallelogram. So, ABCD square maps to this particular shape A prime, B prime, C prime, D prime, where the coordinates for all the endpoints, all 4 coordinates are given like this. So, this completes the present problem. So, in this particular lecture, we had introduced the concept of deformation gradient tensor, its component and physical significance, followed by the definition of both left and right Cauchy-Green deformation tensor with the help of polar decomposition theorem. And we had solved example problem involving this deformation gradient tensor and Cauchy-Green deformation tensor. Thank you.